Hi, this is week 11 of AP Physics, and we're going to go ahead and start Unit 3, which deals with circular motion and gravitation. So for our agenda, we'll be looking at tangential acceleration, introduce inertia, and gravitational force. Next, for our lesson objective, we will be learning how to solve tangential acceleration problems. Students will also be introduced to inertia, and lastly, gravitational force problems. So we're going to go ahead and start with gravitational acceleration. So first of all, tangential velocity, Vt, is a component of motion along the edge of a circle measured at an arbitrary instant in time. So tangential velocity is calculated using this formula. Vt is equal to r times, this symbol looks like a W, is actually lowercase omega from the Greek alphabet. And that is angular velocity. So if you multiply the radius times the angular velocity, that will give you the tangential velocity. Now, if you have a circular motion, for example, we have a pitcher here who's using a circular motion in her arm to throw that pitch. The tangential velocity is when she lets go of it when it goes at the tangent of the circle. So at the instant she lets it go, that will give us a tangential velocity measured in meters per second. Next, in rotational motion, tangential acceleration is a measure of how quickly a tangential velocity changes. So a change in tangential velocity is tangential acceleration. Tangential acceleration is calculated by this formula where you have at, which is tangential acceleration, is the radius multiplied times alpha. That symbol right here is Greek letter A, and alpha is for angular acceleration. The units are meters per second squared. Okay, and for circular motion at a constant speed, the acceleration vector always points towards the center of the circle. This acceleration is called centripetal acceleration, which is centripetal, the word means center seeking. So if you were one of these rides that spin around, which direction are you accelerating? As your back is against the wall, you're actually accelerating towards the center of the circle. Center seeking, again, centripetal acceleration. If you were driving your car and turning and making a sharp right turn like you see in this picture, you're accelerating again towards the center of the circle. So as you turn to the right, it will be accelerating towards the right. Friction in this diagram will also be towards the center of the circle as you turn. Formula, centripetal acceleration, can be calculated using two formulas. It is a velocity square over the radius. That will give you centripetal acceleration. Also, radius times the square of the angular velocity will also give you centripetal acceleration. Now, what if you want to combine centripetal acceleration, which is going towards the center, and tangential acceleration? Well, you would combine both vectors using this formula, which is the same formula as Pythagorean theorem. So total acceleration would be the centripetal acceleration squared plus the tangential acceleration squared, and then you would square root the whole thing to get the total acceleration of an object. Alright, up next we're going to go ahead and do example number 1, and in this example we'll be using this formula to figure out centripetal acceleration, plus we'll also be linearizing that and graphing as well. Example 1 asks us the following question. According to the equation AC equals V squared over R, what is the relationship between radius and centripetal acceleration? Graph the radius versus centripetal acceleration and linearize it if need be. Alright, so we're going to go ahead and be given this data table right here. Here it's on the screen. Here I have it up on the board, the same data. And they ask to solve for the centripetal acceleration. So we have the velocity, we have the radius. Velocity is in meters per second, radius is in meters. So we're going to plug it into this formula right here and solve for it. Alright, so it's going to be the velocity in the numerator, and that's going to be squared. So it's going to be 2. And notice that they keep the same throughout. It's the radius that we're going to go ahead and just make it larger and larger and larger. So velocity squared is 4. 4 divided by 1, the radius in the denominator. So we get a centripetal acceleration of 4 meters per second squared. For our next line, we have, again, 2 put into numerator squared. That's 4. 4 divided by 2 is 2 meters per second squared. This is going to be 2 squared is 4. 4 divided by 3 is 1.33 meters per second squared. And lastly, we're going to go ahead and have 2 squared is 4. 4 divided by 4 gives us 1.0 meters per second squared. Great, so that is our data right here. They ask us to solve for the centripetal acceleration using this formula. We've done that. Next, they asked us, can you please go ahead and graph it? All right, so let's go ahead and do that. So I'm going to graph it right here. In this one, I have the centripetal acceleration on the y-axis and the radius on the x-axis. So I'll be looking at radius, this column and that column. Notice that we kept the velocity constant, so we're only looking at radius and centripetal acceleration. So in the first one, a radius of 1 meter, we had a centripetal acceleration of 4. So that's my data point. At 2 meters, it was 2. So there's my next data point. Next one, at 3 meters, it was 1.33. So at 3, 1.33, somewhere around here. And at 4 meters, you have 1.0 meters per second squared, giving us that graph. And that graph is shows a relationship, shows an inverse relationship. That means as the radius gets bigger, the centripetal acceleration is lessened. So now it is a curved line, so we're going to go ahead and try to go ahead and linearize it. Alright, so how do we make this a straight line so we can make a definite connection that there is a relationship between centripetal acceleration and radius? In this scenario, this is an inverse relationship, right? As the radius gets larger, the centripetal acceleration gets lower. So to linearize it, to make it a straight line, what we're going to go ahead and do is we're going to get the inverse of the x-axis. So one more time, this is an inverse relationship, so we're going to get the inverse of the radius. So given to us, notice in the table was an empty column right there. So that's what it's for. So we're going to go ahead and do the inverse of the radius here. Okay, so we're going to go ahead and start. The inverse of 1 would be just 1 over 1. In this case, it's just 1. Okay, next will be a 1 over 2, so that is just a 0.5. 1 over 3 is 0.33. And finally, 1 over 4 is 0.25. Alright, so I'm going to go ahead and do the x-axis first. Okay, so we're going to start with 0. And let's go 0.25. 0.50, 0.75, and 1.0 over here. So that would be enough so we can get all of these data points here, and that is the inverse of the radius. I'm going to put 1 over r. That's what we're looking at. Here we're going to go ahead and keep the y-axis the same. We're still going to use centripetal acceleration. So that's going to go 0, 1, 2, 3, 4, and that is centripetal acceleration as well, which we have it right here. So now we're going to graph the first column versus our last column right here, and this should go ahead and linearize our graph, giving us a straight line. So let's see the first one. At 1 we have a 4.0, so here we go. Here's 1 and 4.0, so it'll be right here. At 0.5 we'll have 2, so 0.5 is right here. We're going to go to 2. At 1.33 we have 0.3, so 1.33 is over here, and 0.33 will be somewhere around here. And then the last one at 1 we'll have 0.25, so 1 and 0.25 is right there. And you will notice that is a straight line, so we have linearized this problem. So you could definitely say there's a relationship. And there we have it. Our graph has been linearized for problem number 1. Up next is example 2. And in this problem, now we have the same scenario, but the radius is kept constant. Now we're going to change the velocity, and we're going to see how that affects the centripetal acceleration of an object. So, same formula, so we're going to go ahead and square the velocity and then divide it by the radius as per the formula. So it's going to be 1 squared divided by 2, that gives me a 0.5. Next, we're going to go ahead and get this one squared. That will be 2 squared, that's 4. 4 divided by 2 is 2. Next is going to be 3. 3 squared is 9. 9 divided by 2 is 4.5. And finally, 4 squared is 16. 16 divided by 2 is 8. So there's our data. So we're going to go ahead and now graph. We're going to graph velocity over centripetal acceleration here. So we have this graph right here. The range takes care of all of these numbers, so they can fit in there. So let's go ahead and start graphing. So we're going to have velocity here on the x-axis, acceleration on the y-axis. So let's see, the first one is a 1 meter per second. It's going to give you a 0.5, so that will be somewhere around here. Next one's going to be at 2 meters per second. It's going to go ahead and give you 2 meters per second squared, so somewhere around there. 3 meters per second will give you 4.5. So let's see, there's 3, 4.5 will be somewhere around here. And lastly, 8 meters per second, 4 meters per second will give you 8 meters per second squared. So that will be somewhere around here. Alright, so those are our data points. Now we're going to go ahead and do a line to connect the dots. And you will get a nice curve. Now notice it's curving upwards. And different from example 1. Example 1, we had a curve that was going downwards. So in example 1, that it was going downwards, it was an inverse. So we did the inverse of the x-axis. Alright, but in example 2, the line is going up. So to linearize it, we're going to go ahead and do the square of the x-axis. And that will go ahead and give us a straight line. So for this empty column that we're given here, we're going to get the x-axis, which is, the velocity on the x-axis, and we're going to go ahead and square it. So I'm going to put v squared, that's what's going to go in the denominator here for our next graph where we're going to linearize. So get the velocity and square it, that's 1, square 2 is 4, that's a 9, and that will be a 16. So we're going to graph acceleration and on the y-axis, and on the x-axis the square of the velocity, and this should linearize it or come close to. So let's go ahead and get started. At 1, we have a 0.5. Alright, so at 1 will be right here, and 0.5 will be somewhere around that spot, give or take. At 4, we have 2.0. So here's 4, and we go up to 2.0. At the 9, we have 4.5. So 9 will be around here. 4.5 will be somewhere around here. And 16, we have 8.0. So here's 16. We go up to 8.0, and there's our data points. We're going to go ahead and draw a line through it. Now my expectations, it should give me a straight line. It looks pretty straight. Will it hit every single point? No, that's fine. We do a best fit line. So we want it as close to us, hit as many dots as possible. But again, do not expect all the points to be hit. So that's a best fit line. Alright, so there we have it. That was just a hair off. But that's a pretty good best fit line. So there we go. We have linearized example number 2. Up next, we're going to go ahead and introduce the topic of inertia. What is inertia? The tendency of an object to continue in its original state of motion is called inertia. Inertia is directly proportional to the mass. So the more mass an object has, the more inertia we'll have. So let's say this giant boulder, it takes a lot of force to get it to start moving. But once it starts moving, it's going to take a lot of force to get it to stop. Even if it's rolling slowly, it's going to be very difficult to get it to stop because it has a lot of mass. By the way, this picture comes from the scene from Raiders of the Lost Ark. So, next, inertia is based more on the shape. Not just the mass, but also is affected by the shape. So, the formula that you're going to use will be relying on, well, it could be mass times the radius squared for if you just have like a thin hoop. But as you go through it, if you have a solid cylinder or a sphere or a rod, the formula changes. Maybe it's a half times the mass times the radius, or 2/5 times the mass times the radius. So the inertia is actually going to vary depending on the type of object that is rotating. Alright, so you will have to look that up to figure out what is the proper formula for the object that you're dealing with. Alright, now that was just a quick introduction into inertia. In future units we will get more into solving problems using inertia, but right now it's just a quick introduction. Let's go ahead and move along. Alright, now let's talk about a little bit about velocity and acceleration. Could you have a car traveling with velocity towards the positive right and acceleration towards the right? Sure. What would that car be doing? That car would be accelerating. So if both velocity and acceleration are pointing in the same direction, then the car will be accelerating. What about in picture B? The car is going towards positive right, but the acceleration towards the left. Is that possible? And I say, yeah. What's happening to the car? This car is slowing down. Next, going the opposite direction, could we have a car going in the negative direction, velocity, and the acceleration be in the positive direction? Is that possible? Yeah. Once again, this vehicle will be going towards the left, and it will be slowing down since acceleration is going in the other direction. And finally, letter D, could we have velocity and acceleration both be negative, both going towards the left? Yes, and this vehicle will be speeding up, accelerating in the negative direction. Alright, and that's pretty much this diagram. Now let's go ahead and take a look at it from above. Now predicting if the velocity is increasing, decreasing, or staying constant, if you have the acceleration going all sorts of different directions. Alright, so it's best to do it with some drawings. So we're going to have the vehicle here. And in scenario A, velocity is in this direction and acceleration is in that direction as well. What's happening to the car? The car will continue to travel in that direction and the speed will be increasing as well. Alright, so I'm going to put an upward arrow for the velocity. It is accelerating. It's going faster and faster. Alright, now what if the velocity is still in the direction of the blue arrow, but now acceleration is diagonal, acute? What will happen then? The car will go ahead and will be accelerating and it will be turning, but it will be a very wide turn and the velocity will be increasing. Alright, up next, what will happen if the acceleration is towards the center only and the velocity is still towards the right? The car will continue to travel at this constant velocity and it will eventually travel as a circle. This one will eventually make a circle as well, but here the velocity stays the same. Okay, next, what will happen if the acceleration is in that direction, obtuse to the velocity? Okay, so the car will go ahead and take this direction as well, but the velocity will be decreasing, will be slowing down because the x component of this vector will be away from the velocity, so it'll slow it down. Finally, what if the car is going in this direction towards the right, but the acceleration is towards the left along a straight line? It will follow this arrow, but the velocity will be decreasing. So if we label them A, B, C, D, and E, this would be A over here, B would be right here, this is C, this is D, and this will, oops, pardon me, this one would be E. Alright, so that would be the 5 scenarios. Up next, we're going to go ahead and talk about gravitation. In gravitational force, we're looking at the fact that objects with mass will go ahead and create a gravitational field, and that field can go ahead and create force, pulling other objects. So two objects with mass will exert force on each other. So how much force that is, we'll be looking at that using these calculations. So gravitational force is the mutual force of attraction between any two objects. Newton's law of universal gravitation states that every particle in the universe attracts every other particle with a force that is directly proportional to the product of the masses of the particles and inversely proportional to the square root of the distance between them, given as this formula right there, where G is the universal gravitational constant. That value, by the way, for the universal gravitational constant is 6.67 times 10 to the negative 11 newtons times meter squared over kilogram squared. Its name is universal gravitational constant. Again, universal meaning that this constant will work anywhere in the universe, not just on Earth. So these calculations can be done anywhere in the universe. So here's the formula one more time, where you have Fg, which is the force due to gravity. G is the constant, m1 and m2 is the mass of one object and then the mass of the second object, and r squared is the distance between them from the center of the object, not from the surface, from the center of the object. Okay, now we can go ahead and modify this formula a little bit. If we remove the mass from here, that will just give us force of gravity's mass times gravity. So if we take away the mass from here and mass from there, we're going to go ahead and get this formula right there. So on the surface of a planet, force of gravity can be replaced with mg. And if we take away the m1 from this side, 1 from there, then we end up with this formula where we can get the value of g, which is universal gravitational constant multiplied times the mass, here the mass of the Earth, that's why they say E, divided by the radius of the planet squared. And the value for our planet is 9.8 meters per second squared, though for our calculations we'll just go ahead and use 10.0 meters per second squared just to make it a little bit easier. Alright, so weight. The weight of an object depends on how much gravity there is. So weight is the force due to gravity, is mass multiplied times the gravity. So the more mass an object has, the more weight you will experience. An interesting phenomenon that happened to astronauts when they traveled to the moon was the following. Their packs, they were in backpacks, were about 300 pounds here on Earth. Now, how could they carry that? Well, on the moon, it's 1/6 the gravity of planet Earth, so it felt more like a 50-pound bag. Though the mass of it remained the same, either here on planet Earth as it was on the moon. The mass remained the same. The weight was different. It was 1/6 in the moon compared to the Earth, but the mass remained the same. So this pack still had inertia. The inertia of the equivalent of a 300-pound pack here on Earth. So as they walked forward and they attempted to stop, they would feel the beam pushed by their equipment because it had inertia. So you got to put a lot of force to get it to stop. Alright, so that's an interesting fact about that picture right there. Next, example 1. In this example, they're going to ask us 3 parts. Find the gravitational force exerted by the sun on a 70-kilogram man located on the Earth equator at noon. Part B, calculate the gravitational force of the sun on the man at midnight. And part C, calculate the difference in the acceleration due to the sun's between the noon and midnight. And then the values for the mass of the sun and the mass of the Earth will be found on table 7.3, and that is in your textbook on page 228. So when I pick up those values, you know where I got them from, table 7.3. Alright, first of all, let's start with a quick drawing. This is not going to be to scale. So we have planet Earth right here. There's the center of it. Here's our person, again not to scale. And on the other side, we're going to go ahead and have the sun. As I mentioned, not to scale. Alright, and the distance from our planet to the sun is measured from the center of the sun to the center of our planet. So you always use the center. Though in this problem, when it's noon, this person is not quite this distance because, well, it's the radius of our planet. That's going to go ahead and make a difference. Alright, so I do need to go ahead and take a look at that table to get the values that we need. Alright, so for example, the radius of our planet, 6.38 times 10 to the 6 meters. That's the radius of our planet. And the distance from here to there, from the center of Earth to the center of the sun, would be 1.496 times 10 to the 11 meters. Okay, so that's going to go ahead and be the values that we need. Other values that we'll need also would be the mass of the man, which we know it to be 70 kilograms. That was the only value given to us during the problem. And the other ones come from the table. The mass of the sun is going to go ahead and be 1.99 times 10 to the 30 kilograms. Okay, so those are all the values that we need, and again, we picked them up from table 7.3 out of page 228. So we got all these values. Now we're going to go ahead and plug it into this formula. Alright, so we're going to begin force of gravity at noon. So I'm going to go ahead and put an N right here. It's going to be as follows. G, the universal gravitational constant. So that's going to go ahead and be 6.67 times 10 to the negative 11 newtons times meters squared over kilogram squared. Multiply times the mass. We're going to put the mass of the man first. 70 kilograms. Multiply times the second mass. In this case, we want to know how is the sun affecting the mass of the man, so, or the force on the man. So here's the mass of the sun. All of it's going to be divided by the distance between them. So one more time, this distance from the center of the sun to the center of Earth, but our man's not standing on the center of the planet, standing on the edge of it at noon, so therefore it's on this side. So to get the actual value is going to be this distance minus that distance, because we want to know actually this distance. So it's going to be the 1.496 times 10 to the 11 meters minus that distance right there, which is the radius of planet Earth, 6.38 times 10 to the 6 meters. Alright, at this point you go ahead and plug all of these values into the calculator and we will get an answer which will be the following. It's going to be 0.41540 newtons. That will be our answer, 0.41540 newtons. Alright, the next part of this problem, that is part A. Part B, they ask, okay, we want you to do some calculations, but this time it's been 12 hours and now it's midnight and our man's still standing around and he's on the other side of the planet because it's midnight. So 12 hours later. Now, what will be the force exerted on the man? Alright, so for this, the equation will be the same except for one difference. What would be the difference? Rather than subtracting the distance, we're going to add it. Because again, the distance from the center of the sun to the center of our planet, plus the fact that he's on the other side, and that's our radius. So for part B, we'll look the same. And put an M for midnight. N was noon, M is midnight. And all the other values will look the same. The mass of the man is still 70, the mass of the sun remains the same. The distance from the center of the planet to the center of the planet remains the same. But we're going to add the radius of our planet because he is at midnight, so he's further away. So it's going to be plus 6.38 times 10 to the 6 meters. Okay, so you go ahead and you plug all of those values into the calculator. And for part B, our answer is 0.41533 newtons. Okay, so that is our value. Alright, so part A and part B are more or less the same, just the difference is we subtracted. For A, the man was closer, so we subtracted that distance. On B, the man was further away, so we added that distance, and that's the only difference between A and B. In part C, they ask you to calculate the difference in the acceleration due to the sun between noon and midnight. Alright, so for part C, it's going to be as follows. Alright, so we want to go ahead and know the acceleration. So that's going to be force net over the mass. Okay, so the force net is going to be this, the force at noon, subtracted from the force at midnight. So we're going to have 0.41540 newtons at noon and minus 0.41533 newtons at midnight, and divided by the mass of the man, 70 kilograms. And that gives us a value of 1.0 times 10 to the negative 6 meters per second squared, which is a very, very, very tiny number, so it's imperceptible to you and me. Okay, but there is a difference when you are closer to the sun during daytime, when you're further away from the sun at midnight. Up next is problem number 1, and in problem number 1 they go ahead and they add on to the previous example. In this one they ask you, Mars is about 1.5 times as far from the sun as it is to the earth. So without doing any explicit calculations, calculate the gravitational force of the sun on a 70 kilogram man sitting on Mars. So again, they're using some of the data from previously. So for this problem, we know that the force for the man was 0.42 newtons. Now we're going to go ahead and say that he is about 1.5 times further away from the sun than when he was on Earth. So we're going to put 1.5. Don't forget that the radius, though, it's squared. So when we do that, we're going to go ahead and get this number, get my calculator, 0.42 divided by 0.5 squared, and that's going to go ahead and give us our answer. So we're going to round it off to 1.9 newtons. That will be the amount of force felt by the man on Mars. In problem 2, they asked us a similar question to the example. This time, though, is between the man on Earth on the equator and the moon rather than the sun. So during the new moon, the moon is directly overhead in the middle of the day. In part A, they want to find the gravitational force exerted by the moon on a 70 kilogram man at the Earth's equator at noon. Part B, calculate the gravitational force of the moon on the man at midnight. And part C, calculate the difference in the mass acceleration due to the moon between noon and midnight. Now, they also give you the distance from Earth to the moon is 3.84 times 10 to the 8 meters. So here you go, again, from the center of the moon to the center of planet Earth. The mass of the moon is here, which is 7.36 times 10 to the 22 kilograms. Mass of the man is 70 kilograms. And the radius of the Earth is 6.38 times 10 to the 6 meters. So we're going to go ahead and use all of these numbers to go ahead and solve for part A first. In part A, they want the force at noon. So I'm going to go ahead and use the top formula, which is G, the universal gravitational constant, 6.67 times 10 to the negative 11 newtons, meters per second. Newtons times meter squared over kilogram squared. The mass, we start with the mass of the man at 70 kilograms. Next is the mass of the moon, which is 7.36 times 10 to the 22 kilograms. And all of it's going to be divided by the radius, which is squared. So a radius is the distance from the center of this planet to center of the moon to our planet. But we're going to take away the radius of the planet because he is closer, he is on the equator. So it will look like this. 3.84 times 10 to the 8 meters minus, subtract this distance to figure out how far he actually is from the center. 6.38 times 10 to the 6 meters. Okay, so you plug that into your calculator. Don't forget that that is squared. So we're going to go ahead and square that. Multiply everything on top, multiply everything on the bottom, and the answer will be 2.41 times 10 to the negative 3 newtons. So that is for noon. Next, what about in part B where they want it at midnight? Now our man's no longer here, it's been 12 hours, so now he's on the other side. So to get the total distance, remember it's from the center of the moon to the center of a planet plus the radius. So that's going to switch to be an addition. So part B, put an M for midnight, the force at midnight. Everything will look the same. So it's a gravitational constant, mass of the man, mass of the moon, and distance between the Earth and the moon. Oops. 3.84 times 10 to the 8 plus, we're adding it because he's further away, plus the radius of the Earth squared. Alright, you plug all of that into your calculator, you're going to end up with 2.25 times 10 to the negative 3 newtons. Alright, so that takes care of part A and part B. So this is at noon, and this will be at midnight. Finally, part C, they ask you again to calculate the acceleration due to the pull from the moon on the man. So it's going to be acceleration is force net over the mass of the man. So force net is a noon minus midnight. It's going to be 2.41 times 10 to the negative 3 newtons minus 2.25 times 10 to the negative 3 newtons. All of it divided by the mass of the man, which is 70 kilograms. And for that one, the answer is going to be 2.3 times 10 to the negative 6 newtons. Alright, so that goes ahead and takes care of part A, B, and C for problem number 2. Up next is example 2. And here they ask us, an astronaut on a space mission lands on a planet that is 3 times the mass of the Earth and twice the radius of Earth. What is her weight on this planet as a multiple of her Earth weight, which is WE? So I started by putting these two down. So if the planet is 3 times the size of Earth as far as the mass goes, then I'm going to multiply 3 times the mass of Earth, and therefore they'll be equal to each other. Same thing for the radius. They said the radius is twice that of Earth. So I have to multiply the radius of Earth times 2 so I can match the radius of planet X. So here is gravity on planet X, which is g, the constant, times mass of planet X divided by the radius of planet X squared. Now I'm going to go ahead and substitute the values for the mass and the radius of planet Earth, because they did wanted the gravity for planet Earth, how they compare. So I'm going to go ahead and put, instead of mx, mass of planet X, I'm going to put 3 times the mass of planet Earth, divided by Rx. Instead of putting Rx, the radius of planet X, it's going to be double the radius of planet Earth, and don't forget that that is squared. So we end up with this, g is equal to 3 me over 4 re squared. Okay, I'm going to go ahead and pull out the numbers so it looks a little bit clearer. 3 over 4 times g times me over re squared. So what is g times m over r squared? G times m over r squared is just g, but then notice that's the mass of Earth, radius of Earth, so we end up with this. Gravity is 3/4 gravity on Earth. Alright, so if the astronaut has a weight of 1 on Earth, on planet X it will be 3/4. So her weight on Earth would equal 3/4 her weight on planet X. That takes care of example 2. In problem 3, they ask you guys the following question. A volume of rock has a mass roughly 3 times that of a similar volume of ice. Suppose one world is made of ice, whereas another world is made of the same radius, but it's made of rock. If g is the acceleration of gravity on the surface of the ice world, what is the approximate acceleration of gravity on the rock world? So we're going to solve for the acceleration due to gravity for the rock world, which will be mass of the rock world over the radius squared. So here's a relationship. The mass of, you will need to multiply the mass of the ice world times 3 so it matches the mass of the rock world. Okay, but the radius will remain the same. So we're going to go ahead and do that. G multiply times mr, though we're going to replace it with the mass of the ice world, which we need to multiply by 3 so that they're the same. And the radius is the same. So we're going to end up with pulling out the number 3 times g mi over ri squared, which is mass of the ice world over the radius of the ice world squared. So what is g times m over r squared? That is lowercase g for gravitational. So the gravity on the rock world would be 3 times this g, the gravity on the ice world. So that would be the answer for problem number 3. Up next for us is problem number 4. And in this problem you're asked the following question. An astronaut lands on Ganymede, a giant moon of Jupiter that is larger than the planet Mercury. Ganymede has 1/40th the mass of Earth and 2/5 the radius. Find the weight of the astronaut standing on Ganymede in terms of her Earth weight, WE. Okay, so to start this problem, I want to go ahead and make the following relationships. If we would have to get the mass of the Earth and multiply it by 1/40th so it could match the mass of Ganymede. As well as the radius, we have to get the radius of the Earth and multiply it times 2 over 5 with 2/5 so you can match the mass, the radius of Ganymede. So that way, now they're equal to each other. Alright, so now that we have that in mind, we're going to go ahead and do this. We're going to go ahead and solve. They want to know what is the gravity, the weight in Ganymede that would experience compared to that of the Earth. And so we're going to solve for g first. And once we can go ahead and substitute that in, we're going to go ahead and then solve for the weight. So g is the acceleration due to gravity. And here in the additional g's for the planet Ganymede that we're on. Alright, so we're going to compare it versus Earth. So it's going to be gravity of Ganymede is equal to, let's see, g, we're going to use this formula, multiply times the mass of Ganymede over the radius of Ganymede squared. Alright, now we're going to go ahead and plug in the values because we want to compare it to Earth. So mass of Earth is 1/40th, so I'm going to put g times 1/40 mass of Earth divided by the radius, which is 2/5 radius of Earth, and the whole thing is squared. Alright, I'm going to go ahead and take care of the squaring first. So the top will stay the same, 1 over 40 times ME over 2 squared is going to be a 4, 5 squared is a 25, the radius of the Earth squared. Alright, I want to go ahead and pull out the fractions and divide them separately so it's a little bit easier to visualize. So it'll be 1 over 40 divided by 4 over 25. Now what is that? You can plug it into your calculator. Let's do it by hand. Remember that when you divide, it's the same as multiplying by the reciprocal. So we're going to do that. So it's going to go ahead and give me 25 over 160. And if I go ahead and I reduce it, it's going to really be 5 over 32. So this, I'm going to go ahead and rewrite it as 5 over 32 times G times ME over RE squared. So my final answer, I'm going to go ahead and get G, ME, RE and just multiply them together. G, M over R squared, it's going to be G, so that's out for Earth. So it's going to be 5 over 32 acceleration due to gravity on planet Earth. Alright, now let's go ahead and plug that into the mass. So it's the mass of the astronaut times 5 over 32 gravity on Earth. So that's going to give us 5 over 32 the weight on Earth, because weight is mass times gravity. Alright, so that goes ahead and gives us the answer for problem number 4. Let's go ahead and move on to our next problem. Problem number 5, they ask us the following question. It says, which is greater, a Newton of gold on Earth or a Newton of gold on the moon? Okay, so a Newton, how do we calculate that? That it's mass times gravity. Okay, so a Newton is the unit for force, and force due to gravity is mass times gravity. Alright, on planet Earth, gravity was 9.8. On the moon is much smaller, 1/6. So if we're gonna, for the moon, if we're gonna go ahead and reduce G, and we still want it to be 1 Newton worth of force of gravity, then what we'd have to do is increase the mass. So we would need a lot more mass on the moon. So the question one more time, which is greater, the value? And the answer would be the 1 Newton on the moon, because you would need a lot more mass because you have a lot less gravity. So that's part 1. Part 2, they ask you, which would 1 kilogram of gold on Earth have the greater value than 1 kilogram of gold on the moon? Well, since they have the same mass, it's both 1 kilogram, so it would have the same value. Alright, let's go and move on to our last problem. In the last problem, they want a true or false answer. So part A says, no force of gravity acts on an astronaut in an orbiting space station. And the answer for that is false. There is gravity. There is gravity even in the International Space Station. You see them flying around and throughout the space station. How could there be gravity? There is gravity. Alright, and how can you tell? Well, they are orbiting. So here's the space station, and in our space station, there we go, that's my drawing of it. If there was no gravity from the planet, what would happen to that space station? They would just travel on a straight line. Because there is gravity from the planet, they are constantly turning and they're constantly actually falling towards the planet. It's just that their falling rate matches the curvature of the Earth, so therefore they never hit the ground. But they do experience gravity even in the International Space Station. B. At 3 Earth radii from the center of Earth, the acceleration of gravity is 1/9 the surface value. For the answer for that one, true. So if you were to put this formula right here and put a 3 where the radius is at, because they're saying 3 times the radius, we get 1/9. Yeah, because 3 will be squared, so 3 squared is 9, so therefore it's in the denominator, it will be 1/9. So the answer for B is true. Lastly, letter C, if 2 identical planets, each with a surface gravity of G and a volume V, were to coalesce, that means that 2 planets come together to form one bigger one, into one planet with a volume double the volume, the surface of the new planet would be double G. The answer for that was no, it would be false for a number of reasons. Number one, even if you double the volume, that doesn't mean that you double the radius. Doubling the volume does not double the radius. So that immediately throws out the fact that it'll be double G. And even if you were to double the radius, it wouldn't double the radius. You still wouldn't get double G. Alright, so the last one for that is false. Alright, this brings us to the end of our lesson for week 11 on AP Physics. Thank you so much for watching.